Hello there, my name is Sergio Garcia, and I'm going to be doing the extra credit assignment. Right now, I'm going to go over our first notes, and I'm going to go through and do my best to explain them. So wish me luck. So the first thing that we start off with in this lesson is understanding the conversion of units. The reason why the conversion of units is so important is because in physics, there are like three primary units of measure that we hold as our standard. For length, it is meters. For mass, it is kilograms. And for time, we use seconds. And typically, we won't always be given these numbers or these measurements, but it's always helpful to convert to those numbers because that's just our standard. It's just simpler that way. So these questions are used to convert different numbers or different measurements, into our standards. So this first example goes through kilometers per hour, and it changes it to meters per second. That's typically for just a direct length. And this next example is kilometers cubed per hour and meters cubed per second. This is more about area or shape, I guess volume, because it's cubed. So we're going to do one example of our own. If you wanted to pause and look at these, you are entirely able to. But I'm going to do my own example. So let's get started. Let me scroll to the bottom of the page so I have the most room to work with. My drawing tool, and we'll start. This will be example 3. And we will be doing kilometers squared per second into meters squared per second. So we can start off. Let's do a safe number. Let's do 10, right? So we do 10 kilometers cubed. Forgive me for the handwriting. I'm doing this on my mouse. Oh, hold on. Let's make this harder. Let's do kilometers per hour into meters squared per second. Right, so we have our hour right here. We'll do 1 hour. And now we'll do our best to split it up for conversion. So the first thing we'll do here is we'll do 10. We'll hold our 10 right there times 1 kilometer squared over 1 times 1 hour. We know already from our previous conversions that I just skimmed by that 1 hour is equal to 3,600 seconds. And why that is that inside of an hour, you have 60 minutes. And with that, inside of a second, within a minute, you have 60 seconds. So that means that you would multiply 60 times 60 from that hour to get the amount of seconds that you have, which 60 times 60 is 3,600 seconds. Now with kilometer on the top, on the numerator, we have 10 times, and our conversion for kilometer is 10, hold on, 10 to the 3 meters, and we're doing meters squared. So now that we have that established, it's relatively simple. One thing we can do if we want to cancel out is we can take our denominator, that's 3,600, and we can move it 3 decimals to the right so we can cancel out the 10 to the 3. And I'll show you what that looks like after I finish drawing my numerator. Whoops. After I finish drawing my numerator, I go to my denominator, I look at it, right? So there's 3 here, so I can move 3 decimal places left. 1, 2, 3. Now it's smaller. It would be 3.6. 10 times 3 seconds, right? obviously. We can cancel these out. This is obviously 3,600 is the same as 3.6 times 10 to the 3. They are the same number, just written in different ways. We can cross this out and we can get 10 over 3.6. I don't know why the dot isn't drawing. There we go. 3.6 meters squared per second. Now we will divide that with our trusty calculator over here. Excuse that the writing is going over it. I'm using Zoom instead of the other software because I do not have a tablet, but I will just do it right now. 10 divided by 3.6 is equal to 2.7, 7 repeating, or 2.78. So let me jot that down and that will be our final answer. 2.78 meters squared per second. Feel free to check my work. I am still new to this. 2.78 meters squared per second was my answer. I'm still a beginner, I'm still learning. So if you notice that there's anything wrong with my calculation or anything I could do better, I'm always willing to learn. You can comment, you can message me through Canvas. Any of these things are acceptable. So that was our first step for understanding conversions. I'm not going to go into more depth here. I will be moving on to the next topic, but just for future reference, you have those to go on as well as the one I just showed you. Okay, now we're going to talk about a change in position, which is demarked as a change in x. X is typically our variable for position. It's what's most associated to it. So we're going to look at this. Here it says the change in position is equal to x2 minus x1, or your final position minus your initial position. This is typically just to explain distance traveled, essentially, obviously. So it'll relate where you ended up, or your final position, to where you started, your initial position. So as you look at this example, you can see your number line, and it says x1 is at 1, and your x2, I'm sorry, 1 meter, and your x2 is at 4 meters. So what is your change in x? That's relatively simple. So we know that this is your x1 and this is your x2. So again, your x2 minus x1. So you'd have your change in x is equal to your x2 minus your x1. And I'll do this in a different color, just so you can see. What would be a good, let's do blue. So my change in x is equal to my x2 is at 4 meters. I'm just going to write 4 minus my original, which is, or my initial, which is 1. So my change in x is equal to 3 meters. And this is the map, but I can show it to you even more simply on the graph. So if you look back here, you can clearly see that when you hop from your initial to your final, you go 1, 2, 3. You move 3 spots, 3 meters, and your distance between the two, or the distance you traveled, or the change in your position, is 3 meters. That's all pretty simple. And the work was already done here. The way you can visualize it, as shown here, is just a gap between the two. The space in between is your change in x, or your change in position. Here are some other examples. It's important when you do this to understand how vectors work, or which direction you're moving in. You will always move from your initial to your second, your final, right? So if you were, in this case, to move, let me get my vanishing pen. If you're in this case, let me use a different color. If you're in this case, I like purple. to move, let's say your initial is -5 and your final is -3, right? -5 is to the left of the number line, while 3 is to the right of that number. So here's your -5 and here's your -3. If you're moving from -5 to -3, you're moving right in the positive direction, which means that your number is getting bigger and it is pointing positive. In most cases on a graph, positive is typically indicated or is indicated as going right, and the left is negative on a number line. So let's look at this example. I'm going to try not to look at any of these writings too much, but we'll just try it. So let's say your x1 is -3. Oh, this is like the inverse of the last one. So your x1 is -3. I'll do more examples later, don't worry. So your x1 is -3 and your x5 is, I'm sorry, your x2 is -5. So that's simple. You go from your 1 to your 2, your x1 to your x2. So if you go to -3 to -5, you're clearly getting farther and farther to the left. So your rate of change here would actually, or your change in x would be -2. And this goes this way because you're subtracting 2 from your number line. You're going 1, 2 in the negative direction. Let's go through. I'll do one more example over here just to like emphasize. There's most likely more examples down the road. In any case, I'll do them. So let's say you have x1 equals to 4 and x2 equals to -2, right? So we're going to make our number line. I'm just going to scroll it best I can on this line. Say this right here is 0. So we have 1, 2, 3, and 4. And over here we have -1, -2, right? So we know, I'm going to change my color again. That's my x2 is at -2. And my x1 is at 4. So I am going to go from my x1 to my x2 always. So I can count it. I can go 1, 2. Actually, I'm going to do it the way it's supposed to look. This is my change in x. You can very clearly see that it's going left because it's always x1 to x2. And now I can count it out first. 1, 2, 3, 4, 5, 6. So my change in x is in fact like the absolute value of 6. However, we know that it is going left, right? So even though I'm moving 6 units, my number isn't 6. It's -6 because I'm going backwards. My number is decreasing. So I am moving -6. And the math can even show you that. So we know that a change in x is equal to x2 minus x1. So we know our change in x is equal to -2 minus +4. So we know that our final answer will be the sum of -2 minus 4. And our change in x will be -6. Hopefully I explained that well in terms of displacement of x. I'm going to clear my board and we're going to continue to go. All right. So in conclusion, the change of x is equal to x2 minus x1, or your final minus your initial. Always goes from the initial point to final. X1 is your initial point and x2 is your final point. It can't be any clearer than that. So you really don't need a calculator here. These are just simple questions, I'll go through it. I'll even use blue to mimic this. Okay, these are just for green points. So for here, x1 to x2, we know that we are going, my color will change. There we go. So x1 to x2, we're going to the right, plain and simple. Oh, I'm gonna use vanishing pen because I will be going really fast. So we know that for this answer, we are going to the right because this is x1, this is x2. I'm not using vanishing pen, forgive me. Yeah, so over here, going that way. For this one, we are not going to the right, we are actually going to the left. As you see, x1 is on the right, x2 is on the left. So if we're going from x1 to x2, means we're traveling in the negative direction or left. And finally, we have x1 and x2. x2 is on the left, and we always travel from x1 to x2. So we go left. Pretty simple, pretty simple. Let's see if there's more examples. Okay, these are the solutions to our answers. Let's see how right we were. And this one left, this one went right, x to x2, x1 to x2. So it went left, right, left, and left again. So we were correct if you agreed with my answers. Here is just a similar rule to change in x, change in y, which is up or down on the graph. It's the same generic principle when you have a change in distance or a change in y in this case. Typically what you'll see is that your final spot or final position minus your initial position will be your answer for the change in distance. How are we going to define a change in time? Well, time is an independent variable, so it would typically go on our x-axis, and a change in velocity would, be the same way. Just explaining that it's time initial minus time. Time final minus time initial, and velocity final minus velocity initial. All right, now we're going to do some practice problems for y. I'm going to draw these a bit differently than our x ones. I'm going to use like a y-axis, right? So let's say we do this, right? So we have our y1, which let's say is right here, and our y2 is right here. They're 1 and 2 respectively. So our change in y is equal to 2 minus 1. Our change in y equals to 1. Very simple, very, very, very simple. That question, that example, it'd look like this. Change in y. That was likely. A change in y, right? It's not too hard to understand. We're going to go down again and just look through our examples. I'm not going to continue to draw them, but that's like my thought process. I will just do the math. So our change in y here is equal to -1 minus 1. Our change in y is -2, right? Because you'd go, maybe I will draw it. So this is 0. This is 1. This is -1. You go 1, 2, down, right? This is going down, which means that it is negative. So if we go down 2, it's -2. Moving forward, we have the vice versa. So I'm going to actually keep this up. In this problem, number C, we have the opposite occurring. It's the same things, but the x initial and x final are switched. So what that would look like if I erase I'm going to draw a tool back. We're actually going up the number line. Our initial is -1. And our final is 1. So we're going 1, 2. This is in the positive direction. So we're going +2. And I can prove it to you mathematically. If our final is 1 and our initial is -1, it'd be 1 minus -1, or 1 plus 1. Our change in y equals to 2, or +2. And the final example here is your y final being 2. Wait, I'm sorry, this is y initial. Your y initial is 2 and your y final is 1. Very simple question. Once more, y initial, I'm sorry, your y final is 1 minus 2. Your y final is -1. Hopefully you guys understand that. Hopefully I'm doing a decent job. So we're going to move on. Here are more examples, but I feel like we handled it. Oh no, these are just answers. Okay, so observation of time intervals. Time is something that is always moving forward. No matter what, your final time will be bigger than your initial time. You will never have negative time, essentially. And this is what proves it, right? So if you think about it, you can never travel backwards in time. Time is always moving forward. So when we graph time or put it on a number line, it is typically the x value between the x and y. It is independent. No matter what, time always moves forward. And there's nothing you can do to change that, nothing you can do to stop that. It doesn't depend on anything. It moves no matter what happens. So being that is an independent variable, it is again useful for our x value. It says here the second observation of independent variables. Independent variables in function can be the x or maybe the t. Let's call it u. The independent variable in function is taken in a way the change are always positive. Yeah. So it says can be an independent variable where x is greater than 0. If t is an independent variable, the change in t has to be greater than 0. Change in t is change in time. Change in velocity is a change in velocity, blah, blah, blah. It doesn't matter. It doesn't matter your variable. If you place it into the x value, it needs to be greater than 0 because it, it doesn't go back in reverse. And I will hopefully show you some examples. Okay, no, there's no examples, but I'll just explain it. Maybe through a graph. So I'm going to line out and I will use this color. I'll try it out. Yeah, this works. Hopefully you guys can see that. So when you do a position versus time graph, right? So position versus time. This is depicting your relative position depending on what time it is, or in terms of the time, right? So we're going to use change in x as position on, this is our y intercept, right? Our y coordinate field, whatever it's called, our y graph, right? In the y direction. And in our x direction, we will be using change in time. The reason that is because on your x line, or your change in time, time will always be increasing. No matter what, seconds pass and it'll never go backwards. You can't reverse time, you can't change time. Time is constant, right? It can be 1, 2, 3, 4 seconds have passed, but you can never lose time. It'll never be reversal of time. With position, you can go up, you can go up, you can go down, you can go up again, you can go up, 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 up. It doesn't really matter. Your position at that time is what matters on this graph. So change in time will always be greater than 0, time will always increase, but your position can change. You can get closer to something, you can get farther away. It doesn't matter, it's independent. I'm sorry, it's dependent on what time it is. So yeah. Okay, the definition of a slope function. When you have a function y of x, the x is the input and the y is the output. So what that means is when you have your input, x is, again, the independent, right? It goes, this is the x, right? It goes regardless of what the y does. The y, however, it takes the input from the x and it results in an output. So for this position of x, y is here, right? It is on this dot right here. But on this position of x, y is all the way up here. So that's just something you have to keep in account. Y is different on each different value of x. Okay, so for each x, there is a corresponding y. If y of x is like y of 2, that means that whenever x equals 2, you will have a y of 2 that corresponds to it. And that's going to be fleshed out more as I go through. So x is independent, y is dependent. Y depends on x. Or in the position versus time graph that I was explaining, your position depends on the time. Yeah, okay, so it even goes into it here. In the function x of t, t is your input, x is your output, or t is independent and x is dependent. X, which is your position, depends on the time. So here are some examples. It says here that where x of t is equal to 3t plus 1. This is some fun substitution that we can do, so I'm excited to do it for you. Let's use this green color again because I really like it. Okay, so when x of t equals 3t plus 1. So we can see from letter A that when t equals 0, what is x of 0? So x of 0 would equal to, we know that our t is 0. So 3 times 0 plus 1. So our x of 0 is equal to 0 plus 1, or simply 1. Now, why this is, and again, I'll re-explain it, on a graph, for each coordinate of t, there is a corresponding x value to it. So when t is equal to 0, your y is at 1, which would give you the coordinate 0, comma 1. All right, I'll do some more examples. When t is 1, what is the position of x of 1? So x of 1 equals to 3 times 1 plus 1, which equals to 3 plus 1, which equals to 4. So when t is at 1, x is at 4. We'll do one more, and then we'll get into finding the displacement or the change in x. So when t is 2, and the position of, when t is 2, we look for the position of x of 2. So we get x of 2 is equal to 3 times 2, because that's where the t was. Remember 3 of t plus 1. We do the math, excuse me for that atrocious plus sign. 6 plus 1 equals to 7. So when t is 2, x is at 7. So the x of 2 is equal to 7. Now that's all fine and dandy. Now, when it's asking for the change of x, it is asking for x plus 1, I'm sorry, x of 1 minus x of 0. You can see that x of 1 is your final because it is bigger than x of 0. And remember, time always has to get bigger. So no matter what, you can't have x of 0 minus x of 1. That just doesn't work because time cannot move backwards and your position won't move backwards as a result. So it's a change of when t is at 0. 0. I'm sorry, when t of 1 is at 0 and t2 is at 1, what are their relative positions for this question? And I'll show you. So we know from our question that x at 0, I'm sorry, x of 0 is equal to 1 equals 1, and our x of 1 was 4. Let's do the math in my head because I erased. So now we can do letter D and find out. So we know that x of 1 minus x of 0 is equal to our change in x between the 2 points. 4 minus 1 is equal to our displacement of x. Our displacement of x is equal to 3. And that would be our answer for letter D. Sorry if it got a bit messy. And the same applies really for all of these. I'll do these quickly. So x of 2 is 7, right? Let me do this closer actually. So this goes to 7 minus x of 1, which is 4, which equals 3. And this is 7 minus 1, which equals 6. Now, if it's asking for us to graph the function, that's not all too bad. So if I'm going to graph it right here. Oh my gosh, that's terrible. Forgive me, my hands are slippery. Okay, so we have our graph here, and we know that our positions for time and x, right? We're going to get a different color. Oh, no, I'm going to finish my graph first, right? So we know that x is at 0, which I'm going to put right here, 1, and 2. Those are positions of t. So at t equals 0, our x of 0 is at 1. We know that at x of 0, at x of 1, our t is at 4, which I'm going to draw up here. And we know that at x, which I'm going to put like right here. I know I didn't draw the arrow all the way, but you're just going to have to forgive me. We're going to put our 7. So this is our graph. And the way we can calculate slope here is our change in x over our change in t. We can do one point to the other. Let me change my color. We go up from 0 to 1. We are only moving 1. I know the graph isn't proportional. And from 1 to 4, we are moving up 3 units. So if I had to make an estimate, well, let me first do this for all of our points to make sure that our slope is consistent. this is our line. Oh my goodness, I'm going to draw again once more. If I could draw a straight line. There we go. That's about as good as we'll get it. And we'll go back to pink. For this one, we move 1 to the right again, and we go up 3. So if I had to make an estimate of our slope, I would say that our slope is equal to 3/1 or 3. But we can prove this mathematically. So I'll go back to my green color. We know that our change in x is over our change in t, or our change in y over x, which is the original function. We'll get x2, which is 4. We're going to be using these 2 points to calculate it. You can pick any two. You'll get the same answer, as long as you're acknowledging that the bigger number is always going to be your x final and your smaller number is your x initial. So the x for my second coordinate using these 2 coordinates is 4. And my initial is 1 over my coordinate of time, which in the second one is 1, minus my original coordinate of time, which is 0. And we will get 3/1, which equals 2, 3. So we got our answer in 2 different ways. One, just counting using slope, and the other one using our slope formula. When that slope is the velocity meters per second. Oh, okay. And the one thing that I can finally explain is if time is gathered in seconds and displacement, and like your position is gathered in meters, this would be meters over seconds. So it'd be 3 meters per second would be our slope, or our change in position. We are changing, for every second, we are moving 3 meters, essentially. Okay, now that we have that figured out, I will clear my drawings and I will move on. These are solutions. Okay, so the slope is defined as the following. Choose 2 points and find the slope. So it would be, we just did this essentially, I explained it, but we'll look at what the professor had to write. So it is the change in position at the top, or your vertical displacement, over your horizontal displacement, which in this case is our change in time. Right, so this is change in position over change in time. So position is on the vertical line, while time is on the horizontal. So when you have an example like that, let's say you have 0, 1 for your first point and 1, 4 for your second, you can see very clearly that you would replace your second points with 4 and 1 that you got from here, right? So 4 and 1 minus their respective counterpart. This is the x, this is the x, so it'd be 4 minus 1. And here it would be 1 minus 0 for the times. And you get 3, which was my answer from earlier. Okay, so this is a visualization, not too dissimilar from what I drew earlier. This is talking about rectilinear lines. Essentially what you do here to exemplify it on the graph is you get lines drawing on your original, right? So your original would be t1, x1, right? And we'll find that this is over here is t1. You go up this line, and then you go up x1, right? So this is the point t1, x1. This is your initial. And your final, I'll use a different color. We'll use red. No, I'll use something that stands out better. We'll use light green. Your final is T2 distance and X1 up, right? So you start to see how the rectangles form. And the line in between the rectangles is the distance between, or your slope. And you start to get a better picture of how these form out, right? So this would be T2, comma, X2. All right, and we're gonna move on from here. You'll always see the triangle, which is slope. It explains it better here, because it'd be the tangent of this angle, right? Which tangent, if you don't know, is opposite over, let me get my pen. So essentially the tangent of this point right here, oh, I'm not, unless we're vanishing. Okay, so the tan of this point right here will typically give you your slope. And the way that works is because tangent is equal to opposite over your adjacent. Your opposite in this case is this line right here. And your adjacent is the line closest to you that's not the hypotenuse, which would be this one. So the tangent of this line right here would be your displacement formula. Or your slope formula, I mean, which is change in x over change in t. Next, this is just knowing like what units represent velocity. So typically x, or position, is explained in meters, and your time is explained in seconds. Those are the standards that we have. So when velocity is a comparison between your distance over your time, right? Because that's essentially what it is, like distance traveled per unit of time, you will use meters per second. This essentially means how many meters the object will move in that interval of time. And if I'm not mistaken, that's essentially everything that I had to go through on this. Hopefully I explained this well enough for you. If you watch this all the way, I appreciate it. I am doing my best to learn more and more. I appreciate this methodology of teaching. I think I'm learning a lot more from being able to explain it. And yeah, just thank you for your time. It all worked out pretty well. Have a good day. This will be the end of the video.